Hello students, welcome to the second part of our fourth module. So this module is dealing with Fanno flow. Fanno flow is nothing but the flow in which the friction, the wall friction is the sole driving potential for the change in parameters along the flow, right? So it is a constant flow with no work or heat input and what all it is a one dimensional steady flow, right? So we have discussed the assumptions that we are taking while considering the flow as a Fanno flow, right? So the fluid must be perfect gas, okay, there should not be any body forces. All those things we have discussed, and we have also drawn the Fanno line in a enthalpy entropy diagram, right? So governing equations we have discussed. So in the governing equations we have arrived at a conclusion that stagnation enthalpy is constant. So this is a Fanno line, right? So there is a limiting entropy S max and maximum entropy. So upper branch will be proceeding towards S max, and lower branch will also be proceeding towards this maximum entropy value, right? And upper branch will be subsonic, right? And this will be supersonic, lower branch supersonic, right? So students, now I will teach you, or I will tell you about the effect of friction, effect of friction in subsonic and supersonic flows. So how friction affects the upper branch, and how friction affects the flow if the flow is supersonic and if the flow is subsonic separately. So let us discuss about the effect of friction. Okay, so students, let us consider a passage, okay, a frictional subsonic flow of perfect gas through a passage of constant cross section, right? So this is a constant cross section passage, okay. So this flow is frictional flow, frictional subsonic flow, right? The flow is steady with a constant mass flux G. Mass flux is G, okay. Such a flow can be generated by feeding the gas to the duct from the exit of a subsonic nozzle, right? So through a subsonic nozzle we are feeding the gas so that we can generate a subsonic frictional flow. So students, let the fluid at inlet to the passage is at state 1. So this inlet section is 1, okay, and this is reservoir, so this is having the stagnation value 0, 1, and if this is 2, I'm taking another section 2 at somewhere away from the inlet. The H01 will be equal to H02, okay, but pressures may change because this is friction. P01 may not be the same. Stagnation pressure will not be the same as same for state 1 and state 2 because the flow is frictional. If the flow was isentropic, P01 will also be equal to P02, right? So let the fluid at inlet to the passage is at this at state 1 with an inlet flow velocity V, capital V1, okay. So let us depict this situation in HS line. Since this flow is subsonic, so naturally it should be in the upper branch, right? So this should be an upper branch. So let this point be 1. The 1 will be on the upper branch because upper branch will is the branch representing the subsonic flow, okay. So the direction will be like this, okay. So 1 is in the upward flow. So corresponding, this will be H01, corresponding stagnation. And this pressure will be P01, stagnation pressure. And this pressure will be P1, static pressure. Okay. Now, as seen from the energy equation, the stagnation enthalpy H0 for the flow remains constant throughout, right? So this will be constant throughout. If you take a point at 2, a downstream section 2, corresponding enthalpy will be same, H01 only. H01 will be equal to H02, as I have already told you. But what varies? This will be static pressure here, and this will be P02, stagnation pressure, corresponding to the section 2 downstream. Right? So what is happening? What is happening here? When flow proceeds from 1 to 2, what change in parameters is observed? Students, please think of that. How pressure is varied, how stagnation pressure is varied, how velocity is varied. The students, if this is H1 and this is H2, so students, what is this difference in this level? What is this enthalpy? So H01 minus H1. This difference is nothing but H01 minus H1. What is that? That is nothing but half V1 square, right? Right? So it is V1, velocity V is V1 here, velocity is V2 here. So what will be this distance? This particular distance? If this is half V1 square, this will be actually that will be half V2 square, right? Half V2 square. Half V2 square. But students, you can observe that half V2 square is greater than half V1 square, right? Half V2 square is greater than half V1 square. So what does that mean? This means V2 is greater than V1. So downstream velocity is increasing. Velocity is increased downstream. Then what about pressure? So students, in an HS diagram, pressure lines will be like this. So the topmost pressure will be having a higher value. So pressure increase towards this direction. So students, what will be this pressure? P1 will be greater than P2. Means downstream pressure is decreasing. P2 is less than P1. Similarly, P02 is less than P01. So students, due to the stagnation pressure, kinetic energy and enthalpy at state 2 can be observed from this figure. So if you decipher this particular HS diagram, or on referring this figure, you can understand that corresponding to this Fanno line, for an initially subsonic flow. So initially subsonic flow. So initial position was this. Increase in while proceeding towards this direction, naturally frictional resistance is being increased because the flow length is increasing. So the students, while proceeding towards this direction, flow length increases, and friction depends upon flow length, right? The wall, it is actually wall friction. When the wall area or the wall length is increasing, the friction is also getting increased. Friction increasing, frictional resistance increase. So students, when an initially subsonic flow increase, for an initially subsonic flow, increase in frictional resistance with increase in length of the passage causes what? Causes decrease in static pressure, decrease in stagnation pressure, and decrease in enthalpy, static enthalpy. Okay, but increase in flow velocity and entropy. So entropy increases, flow velocity also increases. So students, in subsonic flow, in subsonic flow. What is the effect of friction? With increase in friction, friction increases means static pressure, static pressure, static pressure, static pressure, stagnation pressure, and static enthalpy decreases, but velocity and entropy increases. So two parameters increases and three parameters decreases, right? Right? Okay. So that you have understood. Now students, if we continue through the length of the passage, at some point the static pressure reaches some state called P. Here it is P2. At some state, the pressure reaches a value called P star. P star. At a particular value of static pressure P star, what happens? The entropy will become maximum. So P star is the static pressure corresponding to the state where entropy has reached the maximum value. What? Have you understood? So P star is that particular static pressure value where the entropy of the system reaches its entropy of the flow reaches its maximum value S max. So students, so P star is the static pressure value corresponding to this S max value. So where entropy become state where entropy become maximum, the corresponding static pressure value is P star. Okay, that is P star. So this here the pressure is termed as P star. Okay, so students, if the how flow is how the flow is set in this particular passage by varying back pressure or by varying back pressure value, right? So we have learned what back pressure and all, by adjusting some valve at outlet we can vary. The back pressure is equal to the stagnation pressure, the flow will be there won't be any flow, because pressure at inlet and outlet is same, means there won't be any flow. By reducing the back pressure, flow is set. That idea you know, right? At outlet you have to reduce the pressure, then only flow will take place in any pipe. In any pipe, if you have to start the flow, the outlet valve should be open. So outlet valve is being open means the back pressure is reduced. So students, if you reduce the back pressure of the duct even below P star, if you reduce the back pressure even below P star, in order to follow this line, so the process take place along this line, right? So a Fanno line, if the Fanno line has to continue, if you reduce the back pressure below P star and the process should continue, means it should turn like this and the direction should be like this. But students, it is a violation of second law of thermodynamics, right? Right? Because entropy cannot decrease in an irreversible adiabatic process. Entropy can never decrease. That is an important point. Okay. So this is not possible. So there should not be any decrease in entropy or decrease in back pressure. There should not be any. There should not be a decrease in decrease in entropy after that limiting value, after the limiting point is the point where entropy becomes maximum. After that limiting point there should not be any further decrease in entropy. So students, it can be concluded that for a Fanno flow with the increasing flow velocity, the exit pressure for the duct cannot be reduced below the limiting static pressure P star. So the exit pressure for the duct. The duct for a frictional subsonic flow. Frictional subsonic flow cannot be reduced below critical pressure or P star. P star is critical pressure. Okay, so the pressure will not be reduced, or it cannot be reduced below P star, because reducing below P star means it will be a violation of second law of thermodynamics, because reducing below P star means the entropy should be reduced, but that will not be possible according to the second law of thermodynamics, right? So students, that particular value, so even though the duct discharges into a low back pressure, the exit pressure will be P star itself. No further reduction below P star is possible. Okay. So when such condition is reached, the flow is said to be choked. So such condition, when exit pressure reach P star, such condition is choked. Flow being choked. Flow is choked. So very important. So when the pressure at exit becomes P star, the flow is said to be choked. The Fanno flow is said to be choked. Okay. So the velocity corresponding to that particular point is known as choking velocity. Okay. Choking velocity. And choking velocity is nothing but maximum velocity attainable by a fluid at the exit section of a pipe which is having a Fanno flow. So that is choking velocity. Okay. So students, you understood that particular point. Now, so I have discussed only the upper branch. Similarly, if you take the lower branch, okay, take the lower branch. So similarly, you can have the lower branch. So if this is the lower branch, so for any point in that Fanno line, H0 will be constant. Okay, so I am taking this as a 0.3. So let us 0.3 with the same mass flux G. I am taking the same mass flux G. Okay, so this H03 will be corresponding to this point, right? This will be H03 and this will be H3. Yes. That pressure value will be P3 and this stagnation pressure will be P03, right? So this particular static enthalpy value is H3. Okay, I am taking another 0.4 here. This particular value will be H4, right? Similarly, this pressure will be P4. Corresponding to this will be H04 and H03 will be equal to H04 will be equal to H0 itself, which will be equal to the same H01 or H02 taken in the previous case, because the flow is same only, right? Now you can see that P4 is greater than P3. So since this is supersonic, okay, I am considering a supersonic flow because it is lower. For supersonic flow, when you continue towards the downstream, so this is a downstream section, P4 will be, okay, the section will be like this. So this is 3 and this is 4. This is 4 is a downstream section. So since this is supersonic duct, okay, supersonic duct. Okay, so in P4, if this is static pressure at 4 and this is static pressure at 3, P4 will be greater than P3. So while continuing in a static flow sorry, in a supersonic duct, a frictional flow, a frictional supersonic flow will be increasing its pressure. Will its pressure, static pressure gets increased while flowing through the passage, right? And what about velocity? This will be half v3 square, and this will be half v4 square. So from here you can see that v4 is less than v3, so velocity is decreasing. So static pressure, friction increase, while friction increases in supersonic flow, what happens to static pressure? Static pressure decreases, sorry, static pressure increases, velocity decreases. And what about stagnation pressure? Stagnation pressure, you can see that this is P04. P04 will be less than P03. So stagnation pressure also decreases. Stag pressure also, stag pressure will be increasing, right? No, stagnation pressure decreases. Velocity and stagnation pressure decreases. Okay. Velocity and stagnation pressure decreases because this particular line will be having a lower pressure than this particular line. So students, these are the effect of friction on subsonic and supersonic flow. And similarly, when you reach at this particular point, a P star value, what will happen? The static pressure, when you increase the static pressure to a P star value, it will be the limiting pressure. You cannot increase the pressure above P star. So P star is the limiting value. So that is the maximum possible static pressure in a supersonic flow. You cannot increase above that particular point, because if you increase the pressure above that, the entropy will again start to decrease. So this is the maximum. This is S max. So if you continue the flow towards this, if S max won't decrease. So that is the limiting point. Okay, that is the limiting point. So that particular position is at that particular state, the flow is said to be choked. Okay. Now students, we will be finding the value of limiting Mach number. Limiting Mach number means the value of Mach number at entropy is constant. So now we have to find the value at this Mach at that point. Mach at this particular point should be found out. So how to find out? So students, let us consider an infinitesimal change of state that take place. So this is Fanno line A, B. This is HS diagram. Students, I am taking this. So this is the limiting point C. I am taking a small portion here. Small infinitesimal change of state that take place in the neighborhood of where the point C, the point at which the maximum entropy state, location C, where the Fanno curve changes its direction. So I am taking this small area. So in this small area, we can consider this as a straight line. So here I am taking the portion where the region where Fanno slightly changes its direction. That particular portion you can take it as an isentropic process. Because here it can be assumed as a straight line here. As at that small neighborhood, a very small infinitesimal change of state takes place there in the neighborhood of maximum entropy state, right? So there you can take it as you can assume it as isentropic in this small portion only, because it is almost a straight line in that, vertically straight in that portion, right? So I'm taking here the change in entropy as ds. Okay, so infinitesimal change of state, the corresponding change in enthalpy takes place at constant entropy. Okay, hence for this region the change in entropy ds can be, ds is if this is ds is considered to be 0. That is why I am taking that portion as isentropic. Okay, that at that small particular portion only, that is the assumption. I'm taking very small portion. Okay, so this is the h0 value. Now students, the conservation of mass equation, you know, for a Fanno flow, rho v equal to g equal to m dot by a equal to what? Constant, right? Constant. So students, rho v is constant means if you take differential of rho v will be equal to 0, because constant of differential of constant is 0. So this can be expanded as d rho v d rho plus rho dv equal to 0, right? V d rho plus rho dv equal to 0. So students, from this you can take rho dv plus v d rho is 0 means you can take dv as minus v d rho by rho, right? Minus v d rho by rho. So from energy equation, you know that energy equation is nothing but h plus v square by 2 is a constant, right? Constant. So if you take the differential of this equation, dh plus v dv, right? V dv will be 0. I'm taking the differential of this equation. Now dh is nothing but minus v dv, right? Minus v dv. Okay. So since in the region considered near the state of maximum entropy, the change in entropy is 0, right? So the thermodynamic relation reduces to, so our equation for Tds equation, so you leave that equation here, keep that equation there. Your thermodynamic equation is Tds equal to dh minus dp by rho. Do you remember this thermodynamic equation? Okay, so Tds equal to dh minus dp by vd. Actually it was vdp. Okay, small v means specific volume. This is velocity, this is specific volume. Okay, so small v is different from capital V. In CFF, if you take capital V means it is velocity, small v means specific volume. So this small v can be written as 1 by rho, right? 1 by rho. So since ds equal to 0, because we have taken in this particular portion, we are considering for this portion only. Okay, and this ds is equal to 0, equation will become dh equal to dp by rho, right? So students, if this equation 1, this equation 2, and this as 3. Okay, so substituting 2 in 3, 2 in 3. Where you substitute, you substitute 1 into means 1. Equation 1 is dv. You have got an expression for dv. Substitute dv here. So what will happen? dh will be equal to minus v, again minus v dp by rho. And what will become? dh equal to v square d, this is not dp, this is d rho by rho, v square d rho by rho, right? V square d rho by rho. And now from equation 3, dH is nothing but dP by rho. So from equation 3, dH is nothing but dP, what is that? dP by rho. dP by rho equal to V square d rho by rho, right? So you can cancel d rho and rho, right? So students, what will happen? V square will be equal to dP by d rho, and V will be equal to root of dP by d rho. So students, since ds equal to 0, s is constant for that particular. So this is based on constant s, right? But students, you have already learned in first module. Actually, acoustic velocity A, sound velocity A is nothing but dP by d rho at constant entropy, right? You have learned in the first module, like basic equation. The equation for sound velocity is this one. But now you have obtained a value for velocity at that region as dP by d rho s. So here you can assume that V is equal to A, because this same expression for V and A you have obtained. So it means what? Mach equal to 1. V by A equal to 1, right? So the local flow velocity, this is nothing but local flow velocity. Local flow velocity, right? Local flow velocity, where at this point, at this section V is equal to A. So therefore at that point Mach number will be equal to 1, right? So this equation together with the figure, you can infer that in the case of a friction flow in constant area duct, the entropy of fluid increases as the flow proceeds, and as it reaches its maximum value when the fluid velocity becomes equal to the sonic velocity, which is limiting speed for the flow. Thus, for the upper portion of the Fanno flow, therefore upper portion of Fanno line, V will be less than A and M will be less than 1, and as it proceeds towards right, M will become equal to 1. Similarly, lower portion, V will be greater than A or Mach will be greater than 1, and when it proceeds towards the right, it will reach us the limiting value of Mach number 1, right? Here, so here at this point here, V will be greater than A or Mach will be greater than 1. When it reaches this point, Mach will become 1 or V will become A. So here V will be less than A, Mach will be less than 1. As it proceeds towards the right, when it reaches here, Mach will be equal to 1 and V will be equal to A. So it follows that if the initial velocity is subsonic, the effect of friction is to accelerate the flow. So if m less than 1, friction accelerates the flow, because why? Towards this direction velocity increases, right? So friction accelerates. If m greater than 1, friction decelerates. Friction decelerates the flow to local sonic velocity. So that is the effect of friction. So have you understood what friction does to a compressible flow? So you have understood what actually friction is doing to a compressible flow. If it is subsonic flow, it will try to accelerate it to the Mach value 1 or sonic velocity. If it is supersonic flow, it will try to decelerate it to the sonic velocity. So that is the effect of friction. So students, with this, I am concluding this session. Thank you.